Welcome to my this tutorial live session class. Okay, today we'll discuss about few problem based on linear transformations. Okay, so in my previous class we have seen that one if your linear transformation is only defined on your basis, then we done. We can define for your whole domain. Okay, so today I want to start with one interesting problem. Okay, this one is so please tell me it's true or false. Okay, this question is like that: if you have two vector space, okay, take please tell me it is true or false. Okay, you have two vector space, okay, b and w, b two vector space. B2 vector spaces, okay, and you have one linear transformation T from V to W, one linear transformation, okay, and this one V1 V2 up to Vn, okay, is a linearly independent set of vectors in V. Okay, my question is what we can say about this collection. If you collect this one, okay, where is a V1 is a basis of linear independent set of vectors in V, then what we can say about this set? Yeah, is it linearly independent or not? Please tell me. We are collects this is our collection from your V sets, okay, this is your linearly independent set. So what we can tell about the image of this linearly independent set? Is it will preserved by this linear transformation or not? We are taking one collections from V. Here it is a V, here is W, okay, these two vectors are these two vector space, and this is your map T. Here we are taking one collections, okay, which is linearly independent. So where this is your Vi, we are looking for image of Vi, okay. There was n linearly independent vectors, so we are looking for what is the image of this vector under this map T, and we are taking the collection of this one. So what can we say about this? Is it linearly independent or not? Please tell me. Is it linearly independent? True or false? Please tell me. What is the answer? Please try.
So it will be linearly dependent. So because now if one of the Vi is mapped to 0, no, then that set will become linearly dependent.
No, your assumption is if one of vectors maps to 0, them, without assumption. In general, what we can say? Is it linearly independent or not? What is your answer? Is it true or is it linearly independent? Yes or no? Fernandez, please try. You are going to correct direction. My question is it linearly independent? This collection? This collection is linearly independent or not? Fernandez?
So it is not always linearly independent.
Yes, and others people? Hans, what is your answer?
Sir, actually, I'm not at home, so I cannot turn on my mic more.
Okay, no issue. Okay. Rajesh, please respond. Otherwise, this class will be boring. Risu, what we can tell? Is it really independent or not? What is your opinion? You should respond. Otherwise, it is a little bit difficult for me. Okay, so
I was
fun.
trying to,
Sorry.
sir, I was trying to solve it now.
Okay, so Fernandez is telling this is not always true. Okay, yeah, I agree because suppose try to solve it. Okay, so this is suppose it is we don't know about really independent or not. So what we should do? We should take this collection. Okay, v1 alpha to t of v2. Okay, up to alpha n t of vn equal to 0, where your alpha I from the field set f. Okay, so if all of alpha I is 0, then we done. Okay, otherwise we can't say anything. Okay, so since this is a linear map, so what we can do, we can write this like that: t of alpha I vi, okay, t of alpha 2 v2, okay, up to t of alpha n vn equal to 0. Okay, since this is a linear map, since this linear map, again we can write like that: okay, for all your alpha n. Okay, so now what we can say from here, can we say this element is 0? Then we done, because already your vi up to vn is a linearly independent set. If anyhow we can tell that this is your this sum is 0 for all alpha. Since these all are linearly independent, this force to that all alpha is 0. But can we say this sentence from this one to this one? Is it imply? Is this equation imply to this equation? This is my question. Fernandez? In short, I can write this question. Question is, your T is linear transformation from V to V. If T of x equal to 0, is it imply that x equal to 0? This is my question. Is it imply?
It does not always imply that.
Yeah.
Always.
Sorry?
It doesn't implies, not all time.
Yeah, can you give him one example? Could you please give me one example? Fernandez, you told me the logic. So using the logic, please try to construct one example.
So if we take x is any real number and t is mapping such that t is always map on x 0. So if we put any x in t, then we got 0.
Yeah, you are taking 0 map. Except 0 map, can you give one example? You are taking this one from B to W T of 0 equal to 0 of W, sorry, T of x is 0 of W for all x belongs to W. Yeah, I am agree. Can you give another example? Non-trivial, this is a trivial example. 0 map. Except this one, can you give one example? Non-trivial. Try to use the concept of Fernandez. Fernandez previously you told, na? So if one of the element goes to map to 0, so I am taking R2. Okay. These are basis E1 and E2. These two are basis. Okay. So goes to map.
Then
So you can take a mapping no from R2 to RS T of some xy equal to x minus y.
Yeah, you can take also this one. And in previously you told that if we map this one to 0 and E2 to E2, this also will be work. Is it or not? If it's a map from R2 to R2. In starting you told that if some of element is maps to 0, then this is in your image set collection is dependent. Okay, but here is independent, E1 E2. Is it or not? And since this is defined on basis, so this is Linear transformations. Okay, T of E1 equal to 0 and T of E2 equal to E2. So this is defined on basis, so this is your Linear transformation, we can extend for whole R2. Okay, and this is mapped to 0 and this is mapped to E2. So this is your one example of that T of x, for T of x is some T of x is 0, but that element might not be non-zero. If you take this one, if you take T of 1 0, it will goes to 0. Okay, but this is your non-zero element. Okay, so when you are thinking about example, now try to construct like that. Try to define the linear transform basis. Then it is easy for you. You can visualize properly. Okay, what you need you can define on basis. In starting in fundamentals told that if one vector goes to 0, then what will be happen? This is the case. Here my one vector goes to 0. I am taking that my basis E1 A2, and we define T on basis. Bas is done. We can extend it for whole R2, because every element of R2 can be written as a basis of this element, linear combination of these two elements. Okay. So this is one example. So from this equation to this equation, we can't okay, we can't imply. So what we need, what extra condition is needed to this equation will imply this equation? What extra condition we need? Under what assumptions this equation will imply this equation? Please tell me. What is your guess?
if we take condition that if T of x is equals to 0, then x is equal to 0.
Yes. Everyone agree?
Yes, sir.
Okay. So what is the condition? Our condition is that if these two equation will be equivalent if this map, so image of such vector is 0, it has to force to that x to 0. Okay, we need this extra condition. Okay, and we'll give the name of this. This is your collection from your the domain set, so we'll give one extra name of the collection of those elements. Okay, so we need extra condition that T of image, if image of x under T is 0, it has to force to x to be 0. Okay, we need these extra conditions for implying this equation to this. So now I am to define one class. Okay, kernel of T. Your T is a map from V to W. Okay, this is your V sets, this is your W. Okay, so right now I want to define this class. Okay, how we can define? We can define like that. We want to take element from here, x belongs to V, such that T of x equal to 0. Okay, so kernel of T is nothing but a collection of vectors from your domain sets. So, okay, you have to observe it properly. So we are taking the element from V. Okay, this is your domain set. We are taking the element from your domain set and we are trying to observe what is the image of x. If image of x under T is 0, will that element will belongs to these sets. Okay, so this is nothing but a subset of V. Okay, so one can verify that this is subspace of V. This is very interesting. Kernel of T is a subspace of V. If you collect these elements from V, okay, which satisfy these conditions, so that time this is a subset of V and this is subspace of V. This is your homework. Try to verify. Okay, verify this statement. Kernel of T is a subspace of V. So this was our conditions, that we need T of x equal to 0 imply x equal to 0. Okay, so we need T of x equal to 0 imply x equal to 0 means what will be our kernel? If T satisfy this equation, what will be our kernel of T? Can you tell me? If one linear transformation T from V to W satisfy the condition that T of x equal to 0 imply x equal to 0, okay, satisfy this condition or this condition, then what we can say about kernel of T? What will be?
So it contains 0 element.
Contain 0 element?
So it will be singleton 0.
Yeah.
It contains singleton element.
Yes. This will be this condition force to kernel of T is 0. Okay. Your kernel of, oh my god, what's happened? What is this? Yeah, I'm done. Okay, so, oh my god, yeah, so it's force that kernel, oh, I'm not able to write. What's happened? Oh my god, 1 minute, I am not able to write. Yeah, it's fine. So what we'll get? We will get that kernel of T is nothing but a 0, only 0. If you have one Linear transformation satisfy this condition that T of x equal to 0 imply T of x equal to 0, then our kernel of T will be only the singleton 0. Okay, so this is the condition we need to force that these two equation will be equivalent. Why when I am telling about equivalence? Because if your x is 0, then your linear transforms have to satisfy that t of x equal to 0. Okay, are you agree with me this one, this statement? What is the image of
Yes, sir.
0? Yeah, so if your x is 0, the linear transform have to satisfy this one, that ts is equal to 0. If we assumption, our assumption is this one, kernel of t equal to 0, then other way also it will be true. Then t of x equal to 0 imply t of x equal to 0. So under this condition, we these two statements are equivalent. Okay, so if we assume that kernel of t 0, that time we will get that this equation equal to 0, and since your vi up to vn is linearly independent, we will get that all of alpha I are 0. Okay, means under that condition kernel of t is 0, your linear transformation maps the linearly independent set to linearly independent set. Okay, understand all scenario of this statement? This is the proper statement. Okay, you have one linear transformation from v to w. Okay, and this is your collection of linearly independent sets. Okay, linearly independent sets. If you consider this collection, okay, v1 up to vn, okay, so always it's not a linearly independent. If we assumption the extra condition that kernel of t equal to 0, then your this collection is linearly independent under this condition. Okay, it's fine.
Yes, sir. Fine.
Okay, so could you please tell me another property of linear transformation? Okay, so suppose your v2w1 linear transformation, this linear transformation satisfy kernel of t equal to 0. What we can say about these linear transformations? One thing we can say that t maps linearly independent set to linearly independent sets. This statement we can say, except this one. Try to characterize this t, not characterize, try to find the similarity of this with your functions. You already know about functions. Okay,
Sir,
yeah,
is the converse also true here? Converse, like if kernel of t equal to 0, then those will be linear, those will be alike.
sorry, what is the question, Ravi?
Sir, converse of here, ki if kernel t equal to 0, then the transformation will be linearly independent.
This is the statement. This is your linearly independent sets. Okay, and this is also another collection of, this is another collection of vectors. We don't know about this linearly independent or not. If kernel of t equal to 0, it will force that t of vn is linearly independent. It will force, this statement will force this is linearly independent. If we don't assume this statement, this might not be linearly independent. That time we can say anything about this one. It might be or it might not be. If sum of element maps to 0, then we can't say anything. You can assume this, that is definitely dependent. Okay, this is our
Okay, sir.
yeah, this is our statement. So what can we say about t if kernel of t equal to 0? And what is the difference between our known function to one linear transformation? What is the power of linear transformation? You can see from this statement. So your kernel of t is given. Okay, so try to solve this one. If t of x equal to t of y, okay, for all x y belongs to b, what we can say about t? Please This is my hints. What can we say about x and y? Is this is it possible that x not equal to y and these two images are same under this condition? Is it possible?
Not possible, sir.
Why?
Sir, we have linearly independent, no?
Them?
So if kernel is given to be singleton 0, then this x will be equal to y then.
Yes, because we can write it is like that, equal to 0.
Okay. On the other side.
Yeah. So this is belongs to your kernel of t, x minus y. This satisfies the definition of kernel of t. Okay. So since this is your 0 singleton, it is forced to that x equal to y. So this is your injective function. So if kernel of t is equal to 0, t is your injective function. Okay. So can you give one example of functions, okay, which satisfy this one but not injective? Could you please provide me one example of a function, not linear transformation? If linear transformation satisfies this equation, it has to be injective. So could you please give me one example of function which satisfy these conditions, okay, but not injective? So this is forced to that t is injective. Okay. So I give me one example, okay, where your f satisfy, giving example of functions f such that if your f of x equal to 0 imply x equal to 0, but f is not injective. Okay, but f is not injective. Yeah, please give me one example of functions.
Sir, y equal to x square.
Okay, you are taking r to r, okay, defined by x goes to x square. Okay, so what we can say, if we take f of x equal to 0 imply x square equal to 0 imply x equal to 0. Okay, but it is not a injective, because if you take 1, okay, minus 1, but image is both are 1 image. Okay, this image under f, this image under f, both are 1, so f is not your injective. Okay, so your f is not injective. Okay, so this is the beauty of linear transformation. If you know the kernel, you can tell about is injective or not, and check, and finding the kernel is too easy. Okay, so using this statement we can say that linear transformation is injective or not, because sometime finding checking that function is injective or not is too difficult sometime. Okay, here we can observe that these two under 1 and minus 1 image is going to same, because if you take any positive one negative, okay, same a and minus n, this image is same. Okay, but sometimes seriously it is difficult to find that these two element is injective or not, checking one function. But in linear transformation, beauty is that if you find the kernel, you can tell very easily that is injective or not. This is the beauty of your linear transformations. Okay, so kernel of t have many applications. If you go, this is one application to check. This is a basic application, okay, for math student. If you go try to solve these equations, okay, t of x equal to b, okay, so that time the kernel of t will play the main role here. Okay, because if you know the kernel of t, and if you know the particular solution of this one, you can tell the whole solutions for this system of equations. Okay, so this is the one applications of one of kernel of T. Why we will try to define this T, define this kernel. Okay. Okay, so now I am going to our next problem. Okay, 1 minute. I am so what? Okay, this is one interesting problem. Before going to problem, this problem I want to define another sets. Okay, this is image of T. Yeah, please tell me what is that image of T. Please someone try to define this one. What is the image of T? This is your Lian transformations. Okay, yeah, this is your V, this is your W, this is your transformations. What is image of T? Please tell me, is the
It is a subset of W.
W. Okay, and how we can define?
A set of all T of V such that V belongs to that domain, that is capital V.
Set of all
Small v, no, small, this
W.
T of small v such that,
Okay, you can tell like that. Okay, okay.
okay,
Yeah,
a T
yeah.
of W such that W belongs to capital.
T of V such that V belongs to. Is it fine? Okay, please tell me, image T is a subset of which set? Domain or codomain?
Codomain.
Codomain. W.
Okay. Is it a subspace of, is it only subset or is it subspace of W?
Subspace.
Yeah, try to verify, okay, in home. Subspace of W. Okay. So yeah, I want to mention, okay, later I will mention. Before that, please try to solve this problem. Yeah, so your problem is like that. Okay, this is your domain. Okay, this is your codomain. Okay, this is your V, this is a X. Okay, this to vector space, this is your linear transformation T. Okay, so and take one subspace W here. Okay, so question is, and this linear transformation already okay, no, not okay. Yeah, this is your vector space V, this is your vector space X, and W is a subspace of your V, and one map is given from W to X, not V to X. Okay, this is one, your map is given that from W to X. Okay, so my question is, does there exist a linear map T tilde from V to sorry, this X, your codomain is X. Okay, such that T tilde of W equal to T of W for all W belongs to this is your subspace. Okay, please tell me. One linear transformation is given from your subspace W to X. This is given. This T is given. Okay. Does there exist a linear transformation T tilde from V to x such that image of t tilde on w is equal to image of t, means this is an extension of t is t tilde is a extension of t. If it exists, we will call t tilde as a extension of t. Okay, before that please tell me, does there exist a linear map t tilde from v to x such that image of t tilde on w is equal to image of t? This is provided that w is a subspace of v and linear transformation is defined on w. It's not, t is not defined on whole space, only defined on subspace of w. Can you extend this one? This is my question. Can you extend t to whole space? Before going to this question, I am giving one example. Okay, take one functions. Okay, yeah, take f of x from one to r. Okay, x is this function well defined? Please tell me. Is it well defined, this function? Please tell me, this is well defined or not, these functions?
Yes, sir.
0 is not included in interval.
Yeah, 0 is not included. So
Yes, sir, it is well defined.
well defined.
Well
Okay.
defined.
So this is well defined on 0 1. Can you extend this map from 0 1 to whole R, or at least can we extend this map to this interval? Is it possible to extend this map?
No, sir, it can't be extended because 0 is not defined at 0.
Yes.
Sir, at 0 limit won't exist, no?
Yeah, limit don't exist. So it is not possible to extend. Okay, here. If you think about, if you take one, yeah, please
0
tell.
from real number, then it will.
Sorry.
If we remove 0 from real number,
Yeah, them.
it is defined.
Which one? This map is defined.
So if we remove from real number, if we remove 0 from real number, then it is defined.
Yeah. No, this I agree. My question is, could you extend this map from 0 1 to this one such that your image of this set, suppose take the f tilde is a extension of f. Okay, so this will be satisfied. Is it possible to extend from this interval to this one? My question was that.
Sir, if you define image of 0 separately, so we can extend it. Like f0 equal to 0, and otherwise
Okay,
fx equal to 1 by x.
yeah, understood what you are trying to say. Okay, but if you want to forcefully define is okay. So I am please assumption that this is this will satisfy, this will preserve some property that you have, this is here is continuous. Okay, here it's continuous, so try to assumption that property also, that it's is it possible to extension of f tilde with that assumptions? Understood my question or not?
So can you repeat the question?
So my question was yeah. So Rajesh was telling that if we define this function on 0, okay, that time we can extend. Uh, I
But sir, function is not continuous at
continuous. So my
0.
question is, if we our assumption is this function has to preserve the continuity, that time we can
No,
extend this map from,
no sir.
yeah. So it is
At,
not,
at 0, it's not continuous.
yeah. So that time it's not possible. And I want to mention one thing: if you consider this your v and w all are finite dimensional, all time linear transformation is continuous. Okay, if you can check it, if your domain is finite dimensional and codomain is also finite dimensional. Okay, so we don't think about your codomain. If your domain is finite dimensional, image must have to be finite dimensional. Okay, so this time always linear map is continuous. So here, if this is if we have extension of t to t tilde, it is automatically we will think about that it will preserve the continuity. So here I am impose extra condition. So could you please tell me, is it possible to extend f to f tilde such that it will preserve the continuity also? Okay, that time our answer is
No
no.
sir.
Yeah, we can preserve, we can find one map which will extension of f. So but in linear transformation, yeah, we can extend. Okay, this is the beauty of another beauty of linear transformations. If one map is defined on your subspace, okay, not subset, I am telling about subspace. If one map is defined on your subspace, okay, we can extend it. Understood my point or not? Please tell me. What is the scenario?
Yes
Please,
sir.
please tell me what is the scenario? What is the beauty of linear transformation? Please tell me.
Sir, we can extend the uh, uh, fun-
If one
function which is defined.
on
Yes,
subspace,
yes sir.
yeah,
Sir,
okay. Please tell.
in vector space, we can extend the uh, function from subset to
Not
its
subset,
bigger set.
not subset, subspace.
So if the say the
Subspace,
linear
subspace, sir.
transformation is defined on the subspace, then we can this extend it to the vector space.
Yeah, full vector space. Okay. So how we can extend? This is my question. How? We, which property will we have to use here? In starting my class, I already mentioned that if we know the image of linear transformation on basis, then we done. Okay, and we already know that if we know the basis of subspace, we can extend it to whole space. Okay, do you know these two statement? Please agree with me. Do you know these two statement or not? Please tell me.
Uh, yes, sir. Basis of subspace are same of the basis of vector space.
No, my course, my argument, my claim is we can extend the basis of subspace to V, full space. Not the same. We can extend. My first statement is like that. If you have one vector space, one subspace, this is V, this is W, okay, and if your W1 up to WR, okay, is a basis of W, then we can extend, okay, we can extend this basis, okay, we can extend w1 up to wr, we can extend, we can write like that, we can extend the basis of w to v. That time what will be the basis of v? Up to wr, then add r plus 1 up to vn. Okay, this is one, I think it is well known result. I mentioned in my tutorial class, I don't know, I think you forgot. Everyone agree with me this statement? Please tell me.
Yes, sir.
Fernandez?
Yes, sir.
Okay, this is your one hint, and next hint is, if we know the image of one transformation on basis, then we done. Okay, so try to use these two statement and try to prove this one. Okay, so my question was, does there exist linear transformations from t tilde from v to x such that image of t tilde on w and image of t both are same? My answer is yes. So how we can find this extension? This is my question right now. So use two well-known result. One is we can extend the basis of vector subspace to main space, first statement. Second statement is, if we know the image of linear transformation on basis, then we done. These two statement. Okay, so we can start with that, take w1 up to wr, yeah, is the basis of your subspace w. Okay, then extend this basis to v. Okay, yeah, how we can find that map, how one can find or construct, okay, construct such transformations, okay, linear transformations. Okay, how? First thing is, take w1 up to wr be a basis of w, okay, and extend it. Here I am talking about finite dimensional, okay, you can same proof will follow for your infinite dimensional also, okay, no issue. Here assumption is v and w finite dimensional, okay. You can follow the same proof for infinite dimensional, no issue. Okay, so how one can construct such linear transformation when your v and w both are finite dimensional? I am telling the scenario or the proof. Okay, this is your basis of w, then we can extend this basis to basis of v. Okay, is a basis of v. So now we need one linear transformation from v to x such that image of this one is image of w. So how we can define? We can define like that. Yeah, please send this one to. Okay,
Sir, we can map all element vr plus 1 to vn to 0.
yeah, this is your obvious choice. So you are telling that yeah, at first define on W, then we'll go for vr plus 1 to vn. Please at first define on your this set because we need this one. Okay, so define on wi. What will be your image? Image will be this one. Are you agree? Are you agree or not? Please tell me. Already we know that T is defined on your basis W1 up to
Yes, sir.
WR. Yeah. So we can define T tilde on Wi for all I. Okay, I is from 1 is equal to R. Now define on your Vi. Okay. So define on your Vi. So you are telling that you can map to 0 or anywhere, no issue. Okay. Or we can take one basis of W and map to at least one of the element from basis. Okay, no issue. So we can see that your such T tilde exists, but it's not unique. Okay, because someone can map this one. Okay, R plus 1, take this as J. Okay, less equal to N. So one can map this to 0, one can map this to one vector, one element from basis of your X. Okay, okay, and whatever you can you can map to your some element of W. What is the conditions? T tilde have to satisfy the linearity conditions. Okay, so here easily we can check that T tilde is linear, this condition. Okay, this is a linear transformation. Okay, so this is one unique, this is not a unique T. Okay, this is one construction. We can extend it, we can many such construction we can do. Okay, so here I am giving only one construction, you can do many construction by one. Okay, so this is the existence of your T tilde. Yeah, it's fine.
Yes, sir.
Yes, sir.
So T tilde is not a unique. Okay, there could be many T tilde. Okay, but for finite dimensional case, okay, you can construct all those map. This is one another beauty. For finite dimensional case, you can construct all T tilde. Okay, you can construct by own, because in linear transformation, if you know the image of basis, we done. So by hand you can calculate properly. Okay, so try to do it on for finite dimensional case. At least for R2 you can try it for R2. At least R2, R3 you can try it for R2, R3. Okay, please try to solve all those problems for your confidence, I am telling. So that time you can understand properly. Okay, let's see next problem. Okay, this another good problem is there. Okay, yeah, so oh my God, yeah. Right now we have two linear transformations from V to W. Both are satisfy that kernel of T equal to kernel of S and image of S is equal to image of T, is it imply that T equal to S? Yeah, please try to observe it. This is your V, this is your W, this is your kernel of T equal to your kernel of T S. Try to compare with your previous problem. Here we are telling that if one map is defined on W, we can extend it to your whole V, full domain, such that image of this subspace under T tilde and T both are same. Okay, here our assumption is this kernel of T and kernel of S, means T, your these two map S and T both are same on your kernel of T. Okay, in previous map we told that this T tilde is not unique. Okay, here your S and T both are defined on your subspace and both are same on kernel. Okay, another extra assumption I am giving, that image of S and image of T both are same here. So what we can say about, is it these two are same? My question, T and S both are same or not?
Yes, sir, same.
How?
Sir, because kernel is same and the image also same.
Image also same. Okay, so for the reason I told you, try to those homework at least for basic thing R2 R3. What I told for construction here is not unique. Why is not unique? We can, if we know the image of T on basis, we done. Okay, but when we are transferring the basis to basis, we can send alpha 1 to alpha 1, alpha 2 to alpha 2. Next time we can say alpha 1 to alpha 2, alpha 2 to alpha 1, like that we can cross this one. Okay, here also, but here also we can cross and we can get the same image. In kernel we will what we can do, we will define same things. Means suppose basis of kernel of T is alpha 1 up to alpha, that time we will define same, alpha 1 goes to alpha 1 for T and S, both will define same. But when we are looking for image, okay, rest of the things, here you have many element, suppose here are element in basis, at least few element will be there. Okay, that time we will go through cross. We can, I am giving you one example like that. Take this is T of x equal to x and s equal to 2x. T and s both from R to R. Okay, here kernel of T equal to kernel of s equal to 0, both are same. Image also same, image of T equal to image of s equal to R, but T not equal to s. It looks like, it seems to be same, but it's not same. From this assumption someone can think that these two are same, but not. We can, this is one example, we can construct another example also. Okay, understood?
Yes, sir.
Yes, sir.
Risu?
Yes, sir, understand.
Okay, wait. I am going to everyone are familiar with rank nullity theorem. Everyone are familiar with rank nullity theorem.
So sir, here T and S will be same transformation, no? In this question.
No, I gave one example, na, that T and S not are equal. This is one example. You can construct by your own also. Many example you can construct. This extra assumption it seems to be same but not same. Someone can think this will be same, but it's not, because you can, if you follow the constructions of a previous map, you can understand this two map is not same. Okay, if you with accept this one, you can take this one R2 to R2. Okay, take one T. Our T, I am defined T is like that. Okay, that your E1 goes to 0, E2 goes to E1. This is one linear map, because this defined on your basis. Take S another, take E1 goes to 0, E2 goes to E2. Okay, this is also another linear map, because this is defined on your basis on R, basis or R2. Okay, and kernel is also same. Image of E1 is 0, kernel is also same. Kernel of T will be this form, A comma 0. Okay, where A belongs to R, and this is also kernel of S. Okay,
Yes, sir. Sir,
one minute.
but there,
One wrong is there,
their
because I am
sir,
telling you,
their images are
image
same,
not
na? It
same.
is
Yeah, not
given.
same here. So I am doing this one. Take 2 of E1. Okay, we can do this one.
Sir, but the condition that their images are same, what is the use of that?
No, I am telling that if both are same, kernel and image both are same, that time this map may not be same. This is the our our observation here. Okay, we can think na, that kernel same, image same, this map must be same. We can think, but this is not true. Understood my what is our observation?
Yes, sir. Yes, sir.
This is our observation, that kernel same, image same, after that these two map are not same. This is our little observations. Okay, so you have to observe everything properly. Okay, so do you know about rank nullity theorem? Everyone are familiar with that? Please respond.
Yes, sir.
Yes, sir.
Okay, so I am recall. Okay, rank nullity theorem for your, for completeness or of our lecture. Rank nullity, NULLITY, rank nullity theorem. Please tell me what is that? Please tell me.
Dimension of domain is the addition of rank and nullity.
Sorry, please tell.
So dimension of the domain is equal to this nullity of that linear transform, and dimension of plus the dimension of the image of the transform.
So this is called the nullity. Okay, and this is called your rank. So my question is, you are telling that suppose you have your linear transform from V to W. Okay, you are telling the dimension of V is equal to this one. Is it true for all vector space? This theorem is true for all vector space or not? Please tell me. Is this theorem true for all vector space or some restriction is there?
Finite dimensional.
So your answer is no. Okay, we need dimension of v equal to finite. Okay, so why we need these extra conditions? Could you please give me one example of such vector space that this condition will not satisfy? Can you give me one example? Okay, try to think in home. Okay, this is your homework. Okay, homework is try to find one vector space and Linear transformation such that this condition is not hold. Okay, and I want to tell you one application of rank nullity theorem. Okay, what is the applications of rank nullity theorem? So I am giving one condition that kernel of T of 0 and both and V and W are finite dimensional. Okay, this I am giving this condition kernel of T equal to 0. What we can say about T? T, is it surjective or not? T is surjective. Is T surjective? Please tell me. This is our conditions given that kernel of T equal to 0. Is T surjective? Try to connect with this one. Given that kernel of T is 0 means dimension of kernel of T is 0. So what we are getting?
Yes, sir, it is subjective.
Yeah, we are getting the dimension of V plus 0 of dimension of your image of T. So please tell me how is it surjective? We are getting that dimension of V equal to dimension of image of T. How is it
हाँ, so
surjective?
it is bijective ना sir, मतलब injective and bijective both it is.
No, how is it bijective? It's a question.
Sir,
Bijective
because
means
dimension
injective
of
plus surjective.
images and
So here we are given that kernel of T is singleton 0, no? So that will imply nullity is 0.
Yeah, means it,
So that will imply that this dimension of V is equal to dimension of image of T.
yeah, dimension are same.
That
Is it imply surjective?
Yes, so that will. Yes, that will imply that this image of that T is equal to that W.
Yeah, please tell. You are telling about that image of T equal to W. Is it true? Is it true this one?
sir, if dimension of V and dimension of image are same, so if we take that cardinality of V is equals to cardinality of codomain, which implies that surjective की condition होती है कि मतलब हर एक एलिमेंट मैप होना चाहिए.
No,
तो सर
we have
yes
to
sir,
find
मैं
one
जब
pre-image of from codomain.
यस सर उसकी मतलब कोडोमेन में एक मतलब हर एक इमेज की एक प्री इमेज होनी चाहिए. सर की कंडीशन अगर उसकी कार्डिनलिटी सेम है और वो इक्वल आ रहा है तो सर उनकी होगी कि इमेज कार्डिनलिटी सेम है.
How?
ये हो सकता है सब्जेक्टिव है.
हो सकता है, but it might be,
नहीं
but
सर
is it?
होगा.
Are you sure?
यस सर.
सर अगर फाइनाइट डायमेंशनल वेक्टर स्पेस होगा तो सर ये होल्ड करेगा.
Your T is from V to W. Okay. So your kernelity is 0 and your dimension of V equal to dimension of image of T. So if this imply that your image of T equal to W, then we done. So is it imply? This is my question. Is it imply? We know one result that image of T is a subspace of W. Okay, and we know if we have one subspace, okay, suppose take X is a subspace of Y and dimension are both same, in dimension of X and dimension of Y same, that time we can say that X equal to Y. Okay, understand my point or not? Suppose X is a subspace of Y, okay, subspace, okay, and dimension of X equal to dimension of Y, that time it's imply Y equal to X. I prove that statement in on lecture. Okay, that time we can say. But if your dimension of image T is not equal to dimension of W, that time we can say anything. So what we need extra conditions? Please tell me. Could you understand my point or not? Please tell me. This is your known result. We know that if X is a subspace of Y and both dimensions are same, that time X and Y must have to be same. Okay.
Then extra condition is that cardinality of domain and codomain is equal.
Here please observe this one. Dimension of X and dimension of Y same, that time we can say X and equal to Y. We need this one. We need image of T equal to image of W. And we already know image of T is a subspace of W. So please tell me what is the extra conditions. This is your V, this is your W, okay, this is your image of T. Image of T is a subspace of W, okay, and we need this one, we need this one, okay. So what we need extra condition?
Sir, dimension of image of T is equal to dimension of W.
Yes, we need this one, then we done. Everyone are agree with me?
Yes, sir.
Yes sir.
Issue? Issue, are you agree?
Sir, can you explain this again?
Okay, so what we need? For surjective we need that image of T equal to W. We need these two same, image of T equal to W is, we need this one. Okay, we need. And our statement is that if X is a subspace of y, and both dimension are same, that time it's forced to be that x and y have to be same. Okay, so we already know that image of t is a subspace of W, and we need this have to be same. We need this one. This is your needed, our needed, that image of t should be equal to W. So what extra condition we have to impose on now? That t that will get is surjective. Understand my point?
Yes, sir. Now I understand, sir.
Yeah. So if you have one linear transformations, okay, from V to W, kernel of t equal to 0, and dimension of image t equal to dimension of W, imply t is surjective. Okay, imply t is bijective also, because this is imply your injective. Okay, so one observation is that if we don't assumption this one, okay, only we assumptions kernel of t equal to 0, then it imply t is bijective, where when we will think that t from this one. If t is a map from V to image of t, that time we can think about t is bijective on this one. Okay, when we are think about t is a map from V to your image of t, that time t is bijective on from V to image of t, but not for whole W. Okay, we can think na, since we are taking the this subspace from V, subspace from W, so it is automatically surjective, and since this is a 0, it is injective, this is bijective. If you don't agree with me?
Yes, sir.
Okay, so if you consider this one, V to V, V to V, and kernel of t equal to 0, then please tell me, is it imply t is bijective? Is it imply? Only this assumption can imply t is bijective here. Please tell me.
Yes, sir, it is bijective.
Because what is the reason?
Because dimension of V will be equal to dimension of image of V.
Yeah.
Because your kernel of T is
Is
singleton 0.
singleton.
That's why.
Yeah. So when we are talking about t on V, means your domain codomain both are same. That time if kernel of t is 0, it's enough to imply t is bijective. But for normal function, we can't say about anything. Okay. If t is a linear and defined on same vector space, defined on V, and codomain is also your V, that time if kernel of t is 0, we can say t is bijective. Okay.
Sir, why, sir? Sir, why? Why so?
Okay, so use the rank nullity theorem. Okay, what we will get? Dimension of V equal to, since this is 0, nullity is 0, we will get dimension of image of t. Okay. Okay.
Yes, sir.
Yeah, and we know that image of t is a subspace of your codomain V, and your dimension of V and dimension of image t are same. So it's forced to V equal to image of T. Understood?
So dimension of image of T is V.
Yes. And this one, and this statement also true, that image of T is a subspace of V. Okay, because here domain and codomain both are same. So image T is a subspace of V. This statement is also correct. Is it or not?
Yes, sir, it is subspace.
Okay. And
But
both
why is the
are
dimension of
dimension are same.
image? Why, sir?
Yeah, your kernel of T is 0. Yeah, these are our assumptions. So nullity is 0. So we are getting dimension of image of T equal to dimension of V. So it's force that image of T equal to V. Okay?
Okay, sir.
Yeah, I proved that statement in one lecture. You can follow that video. Okay? So these three are observations from diagonality theorem. So I need one example. Okay? When we are taking domain codomain chain, kernel of T is 0 imply T is bijective. So please tell me, could you please tell me, could you please provide some example where this condition is needed? Otherwise, if we don't assume this statement, that time T is not bijective. Could you please give me one example? And I am giving one hint. Before that, when T or injective, could you guess what is the relation between dimension of V and dimension of W? Which one will be bigger or less? This type of relation I am expecting from these conditions. T is injective means
Dimension of V is less equal dimension of W.
less equal. Is it?
Yes, sir.
How?
So because 1 means every element of domain is mapped with a single element of codomain.
Yeah, no, my question is about dimension. In some sense, your logic is correct. In some sense, okay, you are talking about if I take your functions V to W, that time cardinality of this one must be this one, cardinality. But I am talking about dimension. If F is injective, then this is cardinality of V is less equal to cardinality of W. Okay, so
So this is because no, we are given this dimension of V will be equal to dimension of image of V because T is injective here So that will imply this the dimension of V is less than or equal to dimension of W because the image of V is a subspace of W So
yes.
that will imply that.
Yeah, and in another sense we can tell like that injective means your T, if you take the basis of V, okay, so it's linearly independent. Injective means T maps independent set to independent set, okay, and independent set is the, and basis is the maximal of linearly independent sets. Okay, so we can be extended linearly independent set to basis of W. Okay, so in that sense also we can say, or you are telling that you are using the rank-nullity theorem, using that also you can tell. Okay, so now give me one example that if you don't assume these conditions, okay, are only we are, if you assume only this one, it's not imply that T is surjective. Since T are injective, you have to choose your dimension of V is always greater or equal to dimension of B. Okay, choose. If those are equal, if dimension of V equal to dimension of W, that time we done, because dimension of image of T equal to dimension of V already you know. If you take equal, then image of T and W will be equal. So this is your hints. Try to think. Understand what is your hints?
Sir, can you repeat the hints?
Please tell me, if your dimension of V equal to dimension of W, what will be happen? With this condition that T is injective, okay, means kernel of T equal to 0. This condition is given. If your dimension of V equal to dimension of W, then what will be happen with this condition? We will get, this is your dimension of image of T, we will get from rank nullity theorem. That time this will force to these two are equal. Okay, that time we automatically will get your bijective map. So this is your hints. So
Okay, sir.
you have to take dimension of W is greater than dimension of V. Okay, understand my understand?
Yes, sir, understood.
Yeah. So please try to construct. Take V is R2 and W is R3. Okay, take R2 and your is R3, because we can take here R, because that time we can't get any injective map. We can take R2. If you take R2, then injective imply surjective. So you have to take vector space whose dimension is more than dimension of domain. Okay, try to define T. Try to define on basis. You have two bases, E1, E2, and you need the kernel of T equal to also 0. So these two element can't map to 0. If these two element map to 0, then we will get kernel of T is not non-zero. So map this one is E1, this is basis E1, E2, E3 is a basis of R3. Map this one to either E2 or E3, whatever you can want. So you can check, since we define on basis, T is your linear transformation, and since these two are not mapped to 0, so kernel of T is also is trivial. Kernel of T is equal to 0 only. And here we can see that is not a surjective. Why is not surjective? Why? Please give me example. Please tell me why T is not surjective. Please tell me. What is the image of E3?
So this is because E3 does not have the pre-image,
Pre-image.
and for it to be surjective, no, every element in R3 should have a pre-image.
Yes, this is the logic. So rank nullity theorem, when your domain codomain both are same and kernel of T is 0, that time T is bijective. Okay, and you can take dimension of V equal to dimension of W, that time also it will work. Or image of T equal to image of W, that time it will work. Or you can think, if kernel of T equal to 0 and that time we can think T is bijective from V to image of T. These three things we can. Here we can observe that T is a bijective from R2 to image of R2. If you take image of R2, then it automatically it will become surjective. Okay. So do you have any questions? Otherwise I will stop here.